Hey class, it is Professor Martin at the University of Cincinnati, and we have a Linear Algebra 308 midterm coming up. Had some students ask for some additional guidance on that midterm, so I'm just going to do that really quick. It's 7 problems. I'm going to kind of try to fly through it. Hopefully y'all have been studying, and let's go ahead and just dive right into it. So with this problem number 1, first thing that it's asking is find a nonlinear state space model of the system x equals f of x u, where x is equal to I vc to the power of t. So we need to use two things for this. We need to use Kirchhoff's voltage law, and we need to use Kirchhoff's current law. So for problem 1, we need to use the voltage law. It's going to look like this. So Kirchhoff's voltage law equals U. So U is equal to voltage and resistance, plus voltage law plus voltage current. Voltage law equals U minus voltage resistance minus voltage law equals L derivative of the integer over d of f. So that's basically saying that given the input equals to be plus BL plus BC equals. So for part B, let me erase this. That's not very fast, is it? Let's try something else to erase this. Can I do this? Sorry. I'll try to erase while I'm reading. Assume that a fixed input voltage is given. Okay, that's good enough. Assume that a fixed input voltage is given, i.e. U equals U, and the power is fixed. Obtain an equation for the equilibrium points I and Vc as a function of the circuit parameters RL, Cp, and U. This should be in your notes. We actually went over this point specifically, so I'm not going to do that one. I do have my notes to the side of me here. So the rest of these points, I haven't got these yet, but I will do this. We can move on to the next question. Next question here. And okay, so for this question, pretty simple stuff. So for the set of all n times n skew symmetric matrices, i.e. the set V equals A E W, basically what you need to know is that W means the set of all n by n matrices. So let's pull out the pencil. So for 2A, so V, the vector, A, Mn is such that A to the power of T equals negative A. Because vector space V, and the reason that is because vector space plus is equal to vector space is equal to negative vector space. V does not equal vector space. So in this case, I might just type this out. So that's what I got for A. Actually, there's one more part. So the vector space for closure under addition and multiplication, A, B, E, W, so A plus B to the power of T equals negative. Here, let me write it down so you can see what I'm saying. A plus B to the power of T equals negative A plus B to the power of T. So that's just for 2A. And let's try to go to... erasing this is taking forever, so I'm just going to do this. I'm just going to bring the questions in again. So the question here, the set of all n times n diagonal matrices. So this one's tricky. This one is tricky. I understand why people had questions about this one. So let me try to explain this the best I can. Vector space V is defined as all matrices A that exist within Mn such that the transpose of A is equal to negative A. So if you don't know what that means, I can go ahead and draw that out for you. So we're doing B right now. So V vector A E W, or sorry, and sorry, it's kind of bright in my room, so that's why I was making so many mistakes, I think, the light. So AEMN is matrices are diagonal. So this is the part that's tricky. So if you didn't get this, I'm going to try to draw this out for you. I have my notes here. This might take me a minute. So yeah. So that's the answer we're looking for. This is the answer that we're looking for right here. And then, of course, energy, watts, and 0 matrix exists. So vector does not equal that. C, that should be in your notes. If I were to, essentially all that you need to know is for C, it's a subspace. Sorry. It's a subspace. That's all you need to know. Let's move on to question 3. Okay. So for this one, we need to use a reduced row echelon form of S. If you don't know what that means, should be in chapter 9 of your textbook on echelon rows. Okay, so here's what you need to know. Try and fly through this. Not making very good time. So 0 equals 0 minus 2. That's impossible. Zero equals 0 minus 2. That's impossible. You should know that. Hopefully you know that if you're in Linear Algebra 308. So 0 over 0 x1, x2, and then I'm running out of space there, but ER squared. So the subset is therefore not a subspace. So that's for 3A, not a subspace. just mark that. I'll just mark that. Or sorry, 3a. 3b is actually a little bit simpler. So S equals x1, x2, x3, EIR, or sorry, I'm misreading my own notes. ER cubed is such that x subscript 3 is equal to, of course, x1 plus x2. 1 plus 2 of R3. And I'm kind of running out of space there, and I haven't quite figured out how to erase stuff very easily, so I'm just gonna do my little trick. Okay, so still working on B. Let x yes so let x yes, so x, and then and x1, x2, x3, y1, y2, y3, EIA, basically. Here, I'll type that out. x1, x2, x3, y1, y2, y3. Yeah. Closure under addition. You get x3 plus y3 equals x1 plus x2 plus y1 plus y2 equals x1 plus y1 plus x2 plus y2. So x plus yes. So basically, the takeaway here is x 1, 2, 3 plus y1, y2, y3 equals yes. That's the main takeaway from that. We can say S is a subspace of IR cubed. Okay. So that's basically it. Nothing too crazy on that one. Hopefully that hasn't melted your brain too bad. Let's see. Let's go ahead and go to next. So problem 4. 4C. Show that S is a basis. So for 4A, you can just use MATLAB. For ref S equals 100, 0, 1, 0, 0, 0, 1. That's a binary matrix. So for A, use MATLAB. Uh, 100, 0, 1, 0, and 0, 0, 1. So it has 3 pivots. Using MATLAB, inverse S. Sorry. Jeez. Inverse S. Inverse S, -1, 2, -1, 0, 1, 0, -2, -3, -1. Should do the trick. So that means that S is invertible as well. So it's definitely a basis of IR3. I'll type that out. So for B, same deal. Just use MATLAB. Yeah, for 4B, use MATLAB, NRER, V, another matrix, and it is also invertible as inverse vector space half, -1/2, -1/2, 2, 1/2, -1, -1/2, 0, 1/2. So it's also a basis of IR3. So both of these basis of IR3. For C, it's a simple system of equations. Hopefully, so this is another one where you can use MATLAB. I'm going to have to do my little trick here, because this is going to take me a second to actually draw out here. So, okay, so for C, pretty simple stuff. So V vector is equal to 4, 2, and 9. We know that. EIR3, comma, V equals amps, comma. So we have some columns here. 1, 0, 2, plus amps sub 2, one, 1, A3. So I want you to think about what is something that you've noticed about all of these equations. Something that I hope that you have noticed from my classes from all of these equations, which is that basically if you have a variable such as A1, A2, A3, it's nearly always equal to or not equal to another variable 1, 2, 3 respectively. So in this case, if we put the v in the brackets, s is equal to, and then in the brackets, we're gonna consolidate the math that we've done up here. So A1, A2, A3. So 429 again. Is equal to A 0 negative 2A. That should make sense. Plus A2 and A2 plus negative A3 0 A3. So 4 equals A plus A2 minus A3. Remember that. You need to get your signs right. And then 2 also equals A. Sub 2. And then 9, in this case, is equal to negative 2A. So it's basically a logic problem. Plus A2 plus A3. So using MATLAB, A equals negative 7 over 2. A2 equals 0. A3 equals 5 over 2. So vector space sub vector equals negative 9 over 2, 0, 5 over 2. And that one is hopefully it was pretty simple to you guys, because we went over that in class a shit ton, and you guys always raise your hand asking me questions when I had literally just answered the question. And you wonder why I grade you harshly, and it's because in class, very clearly, I'll be there very clearly saying V equals 429 EIR cubed. V equals A 102 plus A2 111 A3 negative 101. And you don't listen. You don't listen. And you try to do the homework. I look over the homework, and I'll just say, hope you have a backup plan. Hope you have a backup plan. For D, all I'm going to say is vector V with respect to the basis of V. That's all I'm going to say. Let's go ahead and go to image 6. Or problem 5. So problem 5, I'm not even going to do any math for you. Well, I'll write this out a little bit. So x1, x2, x3, x4. So that's a column of x's. So negative x3, x3 plus x4, x3 again. So that'll end up being 6. That equals x3. We get another column. Plus x4. And again, guys, if you haven't caught on to this yet, let's think about this. X 1, 2, 3, 4. And then we take 3 away, that's 1. So here, I'll write this out. So from this, we end up with X 4, 5, 6, 7, 8, 9, 10. So this is equal to X10. So X10 is equal to negative X3. So right now we have negative 3X. But then we add X3 and X4. So now we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's 3. So negative 3 plus 3 plus 4 plus 3 plus 4 equals X14. So X14 equals X3 and then plus X4. So we end up with 14, 15, 16, 17, 18, 19, 20, 21. That being said, since these vectors are non-zero, and clearly they are linearly independent, as they cannot be written as clear scalar multiples of one another, it can be said that they form a basis for IR quadrupled. Or that negative 1, 1, 1, 0 span IR 4. The big takeaway from this, I'm going to write this out. The dimension of S is 4. So nothing too crazy. Like I said, gonna fly through this. Okay. Question number 6. I'm still working on it. I'm still working on question 6. So we're going to go to question number 7. So for A, this first one, X EV, if X can be written as a linear combination of Y1 and Y2. So using MATLAB, I'm going to change the color. A equals 2. A2 equals 3. Okay. So x equals column. Okay, we're seeing the columns again. 8, 2, and 11. Now that equals 2. 1, 1, 1 again. Gonna add 3 from here. So we got 3. Two, 0, 3. And you may be asking, where did we get the 2 from here? The 0 is understood. It's understood that it's always there. So x e v. Let me erase this. Is there a easier way to do this? We have enough space. We have enough space. So 7b, super simple. Basically all you need to know, x of vector is equal to 1, negative 1. So x is equal to special 1. And then again, we see this all the time in linear algebra, 1, 1, 1 minus negative, or minus special 1. See this again, linear algebra 308, we get 203 is equal to negative 1, 0, and negative 2. And that's basically it. So things to remember is in linear algebra you see the column 1, 1, 1 all the time. And you see 2, 0, 3 all the time. Make sure to use MATLAB. Make sure to use that. Use MATLAB. If I need to make it bigger, well, use MATLAB. So those are all the all my notes for linear algebra 308 at the University of Cincinnati. Hope to see you in class tomorrow. Midterm is on Thursday, and Thursday will be the 9th, November 9th, 2023. Hope you guys have a great